Good morning and welcome back to our channel. We're continuing with our fixed cycles, and frankly we're moving on to the last fixed cycle in the Fanuc environment. But you'll also find it elsewhere, namely the fixed cycle for making grooves. There are two fixed cycles because we can create grooves either along the diameter or on the face of the workpiece. Let's say this is our 0 point. So we can enter with a cutter of diameter x from x plus to x minus and create a groove which is the standard groove you might find, I don't know, on a piston, for example, the grooves for the rings, or a front groove, which is basically a slot, so a groove carved at the front of the workpiece. The concept is the same for both macros simply. This one will be called G75 and this one will be called G74. Let's start with G74. For the simple reason that we've already encountered it, specifically regarding deep drilling cycles with the chip breaker. If you think about it, grooving in this way is somewhat like making a hole for the machine. It just won't be a hole relative to the axis, and it will be a hole that can widen, because if I need to make a groove of 4 with a 4 insert, I certainly don't need a macro to do that. I just go in and then come out. However, if I need to make a groove with a 5 tool, where the width from here to here or from here to here is 30 or 40 millimeters, it's obvious that I need to groove a lot of times. Therefore, macros or these fixed cycles help us a lot. Unfortunately, these fixed cycles have a drawback. They weren't designed for creating chamfers at the ends or fillets. I don't really love them much, and lately, since machines are starting to have positive uses, I'm using conversational programming, but it's good to know them. Later, I'll add some videos that won't be numbered like the ones I'm doing now, but there'll be exercises that will allow us to tackle all these topics in a more practical way. Alright, let's start now with G74. Let's say I've already called the tool offset and I've already entered my cutting data. I'll just show you. Let's put it as a title. I'll just show you the main things to do. Basically, let's assume we need to use a grooving tool to essentially create a groove that starts from a diameter of 116 mm, goes down to a diameter of 30 mm in essence. I'm giving you a practical example. I'm clearly copying it. Its depth is 12 millimeters. Alright, so what we'll do is call a tool offset as always. It could be T0303. We'll position ourselves where G0, X116. Let's always turn on the water because when you're grooving, water is really important. The problem with grooving is actually the breakage of the cutting tool at this point, and I'll be working with this perfect virtual point. Now we need to enter G74, R1, then G74. I'll write it down for you now, and then I'll explain it. X40Z3. 3. Co 16 Z5G. 7 4. 1G 24, X40 Z 12, 40 Z 12, X40 ZX. The value of F is around approximately 0.05. So, what does all this stuff mean? All this stuff means R1, the tool retraction distance indicating 0, which means there's no retraction. What does it mean? As the tool goes down, it will make small stops and come back up. Of how much it comes off by a millimeter. So, it doesn't take a straight path from Z5. Well, Z5 is a bit exaggerated, let's say, from Z2 to Z12, but it will follow a path where every Q, so every 6,000 thousandths of a millimeter, the machine will go back by 1 millimeter and then start again. This will allow for the breakage of the chip. Personally, I wrote $6,000 for a slightly flat surface, for example, but I wouldn't say more than 3,000 tiles over a length of 12 to 116 diameter with a thickness of 5, because I want to break the chip. Well, 4,000. What does that mean? What does P4000 mean? After I've made this movement, Zakate, 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 I've reached Z12. I go back and move down by how much? By 40 mm. P, throat widening distance, expressed in thousandths of a millimeter, without sign. Why without sign? Because it's X40. That will tell it where to go, meaning I want to go. From X116 to X40, so it's X40. That will determine which way to move X40, not 30. Because we have to take into account the diameter generated by the thickness of the tool. So 5 min on the radius means 10 mi in diameter. So this time, this cycle will make small stops. Go back by 1 millimeter. Go all the way down. Come back to Z2. Move over here. Go forward by 1 millimeter. Come back. Go forward to Z12. Return to Z2. And do all this stuff until I reach X40. The distance from here to there isn't a multiple of 4,000, so the last movement could be just 1 millimeter or 1.5 millimeters. This isn't a problem for the machine. What matters is that it works from X116 to Z30, obviously. We need to keep in mind that our grooves usually have chamfers here and here, and sometimes radii, which can be a problem. So we have to take this into account when programming this macro, because compared to the finished groove, we should leave some excess material on this thickness. This isn't a problem, but we also need to leave enough excess material so that this potential radius isn't, let's say, cut off by our cycle. Therefore, the final part, we always have to program in ISO X and Z, X and Z, X and Z. Once this nice cycle is done, we need to position our tool here to make a path like this. In fact, usually you do the chamfer, go down, make the radius if needed, stop just beyond the midpoint, go up, come back, get here, do the chamfer, go down, make the radius, and go up beyond the midpoint. So, be especially careful when these radii are very large, because as long as we have an R1 with some excess material, instead of writing 116, if 116 is the final dimension, we'll write 115. Instead of writing 30, we'll write 31, and we'll be higher up. Instead of 12, we'll write 11 if those are the final measurements. After that, we'll create our profile. That's why the groove macro isn't a very big macro. Another thing is, if I have more than one groove, especially on the radial ones, I need to write more macros. So I have to move and reposition myself repeatedly. This macro doesn't allow for the execution of 2, 3 or 4 identical grooves. Let's look at the G75. The G75 is exactly the same thing. So G75, obviously I work from X plus to X minus, meaning going down, but the macro can also work going up. It's a matter of choice. It's clear that if we want to effectively clear the chips, working from large to small is always better. Well, let's say that now what will change won't be the X anymore, but it will be the Z. So if I have this 0 and I, let's say, reflect. Let's take this example. Here I have a diameter of 150, a groove width that goes from 25 to minus 25 and from Z minus 7 to 9. It's coming out wrong, it's a mess. So the diameter of the part is 100. 70? No, it's coming out wrong. It's a mess. Distance from here to here, approximately 10. Distance from here to here, approximately 30. Throat, depth, diameter, approximately 80. So, what changes? Basically and essentially, the X and Z coordinates undergo modification, and then these change based on our tool widths. So with my specific tool, I'll position myself. Let's say it's always a thickness of 5 mm. I'll position myself here. X at 102 mm, Z at 10 mm, where 5 is indeed the thickness of this insert. Z minus becomes 15. R1 consistently remains fixed at pulling distances when it halts momentarily, before going back to start again anew. X transforms into what we call as bottom groove level, thus making it X equals precisely 80 millimeters, while bringing Z right over here. Z minus 30 in totality. You see clearly now how our groove still measures 20 millimeters wide, but shifting occurs from 15 up till 20 millimeter mark. Less than 4 thousandths insertion depth, obviously indicating directional shift therein. Then proceeding downward, 3,000 units each time, detaching repetitively until returning upwards once more, followed closely thereafter by another shift equating exactly 4 thousandths per 4,000 measurement scale, applied accordingly throughout entire process, seamlessly transferring concept previously established within front-facing grooves earlier onto radial work naturally. I can't do the chamfers here either, so I'll have to strategically and carefully plan for some over metals, unless I need to make some rough grooves. I'll have to plan for some lateral over metals, the bottom of the groove and the sides to make chamfers and any radii, and not leave any indentations. So in the end, I'll also have to make my pleasant and efficient movement up to the middle of the groove, come back up, make my pleasant and efficient movement up to the middle of the groove and finish it off. There we go, we've covered all the fixed cycles that can be tackled. Obviously we've gone through them a bit roughly because we've taken them one by one. Now we'll examine a few things that, when integrated with the fixed cycles, help the programmer do some nice work. So we'll transfer all this to the simulator, and we'll do some exercises on the Fanuc simulator and the Siemens simulator, keeping in mind the limitations of each. For example, the Fanuc simulator doesn't allow for direct programming of angles, meaning one angle at a time, while unfortunately Siemens doesn't support macro instructions. Since we want to become skilled programmers, we'll train on both. A little thing, for example, when I had my little workshop, I created a sub-program for managing grooves. And what is a sub-program? Let me give you a little preview. The sub-program is this. It's my main program with all the things I need to do, and in another part of the memory I have a sub-program, which is a little program that manages certain tasks. It can be called within the main program, so the main program reads the sub-program and then goes back to read the main program. I had created little programs for the grooves where I kept the cutting parameters fixed, but I could still call and modify them whenever I wanted. I had included all the X and Z values as parameters, meaning I identified them with letters, and I made a finishing cycle using letters, inserting width and depth. So for depth I entered not the diameters but the depth and the starting diameter. This little program handled the whole macro process for me. Additionally, I ensured that every step was meticulously documented in a detailed manner to avoid any potential errors. I could repeat it 10 times by moving the origin by 20 mm or 15 mm, approximately millimeters or 50 mm in length. This discussion explores parametric programming and CNC calculations. I can set variables like A, B or C. A program variable prompts a choice. We enter the Fanuc simulator to demonstrate our macro. A workpiece of 150 mm diameter and 80 mm length is set. Parameters and a T0505, a 4 mm grooving tool, are called. Copy the example. What happens if, say C? What happens, for example, if I've made 10 grooves, counting the 10th, and I've set a program variable that says when you've made 10 grooves? Make a choice. It becomes interesting, really interesting. Now let's jump into the Fanuc simulator for a second and create a groove like this to show you how our macro works. Okay, so now I'll pause the video for a moment and pick it back up in a bit to enable my simulator. Here we are in front of our simulator. I've set up a workpiece with a diameter of 150 mm and a length of 80 mm. I've set my parameters and called a T0505, a 4 mm grooving tool, but let's copy the example. You see that this example? No, let's not copy it. Let's make it a bit different from this example. Actually, no, let's copy it because otherwise you might not find it. So, a grooving tool of... Alright, let's go into edit mode for a 6 mm grooving tool. Format error, because we're doing it this way. Obviously, the machine's comment doesn't give any information. It's us who need to go into the tool table and tell it, look, T05. Copy it. Edit 6 mm grooving tool. Format error occurs. Machine's comment lacks info. Update tool table. Look, T05. Ignore virtual point. Bottom radius irrelevant for grooving. Are you an insert or mounted groove tool? So, let's go into edit mode for the 6 mm grooving tool. Format error, because we're doing it this way. Obviously, the machine's comment doesn't give any information. It's us who need to go into the tool table and tell it, look, T05. Alright, the virtual point in this case doesn't matter. The tool's bottom radius. Let's get used to putting that in. But for grooving, it doesn't care. And we say, alright, what are you? Are you an insert or a tool for grooves mounted? Alright, the virtual point in this case doesn't matter. The tool's bottom radius, let's get used to putting that in. But for grooving, it doesn't care. And we say, alright, what are you? Are you an insert or a mounted tool for grooves?
Position 1. Width 6 meters. in depth. And you can see it drawn approximately 6 meters. Let's close this and start carefully giving it the cutting data. So, for the cutting data, we can very easily do the grooving in G96 at 100 meters per minute, M4, smoothly and efficiently. We're using the advanced keypad with precision and accuracy. So, let's go to G0, X, diameter 150, we give the 152 meter of safety. So Z, we have A, minus 31. Pardon, minus 25, set to minus 31, which is groove side position minus tool thickness. Z is minus 31, positioned left. Insert G75 R1. G75 R1 is a standard parameter. Pull away by at least 1 millimeters when breaking the chip. G75 X bottom of groove 124, 75 X bottom 124.4, 175 X bottom 124.4, 125. Here, Z is the groove side. The tool's angle reaches the groove. Z is minus 70p. Break chip at 3 millimeters, move 3000. Shift Q for visibility. 6 is thickness, 5000, 5 millimeters. Insert F 0.1 EOB. F is feed rate, then exit groove, set G0X. 75 to 24, 175. Z, in this case, I need to stop saying at this particular point in time because I'm just hindering my own progress. In this case, Z becomes exactly and precisely the groove side because that's the specific angle of the tool that will reach our groove. So Z is minus 70p, which is the exact depth at which we want to break the chip, approximately 3 millimeters. 3000 is the precise amount we want to move. As you can clearly see, I can't see the Q, so I need to do Shift Q. 6 is the overall thickness, approximately 5000, 5 millimeters, and then we insert F.1. EOB insert. F is the specific feed rate at which we will make the cuts, and then subsequently we will exit from the groove, so let's set G0X. End of business. Insert M30, EOB insert V. Now we are fully prepared and ready to proceed with the simulation process. Before we begin the simulation, I will attempt to rotate the view if it is possible. Let's navigate to the simulation section, and here we are ready to start. Initiating the rotation process now. Notice the unprogrammed feed rate as it begins. Let's pause the simulation for a moment. We will now proceed to the edit mode. In this mode, we will carefully insert the command F0 This command is crucial for the next steps. Ensure that all parameters are correctly set before continuing. Once everything is verified, we can resume the simulation with the new settings in place. This will allow us to observe the changes and ensure everything is functioning as expected. If any issues arise, we can stop and make further adjustments as needed. Let's proceed with caution and attention to detail to ensure a successful simulation outcome. Let's delete this and go back to simulate. So what happens? In reality, F01 can be inserted exactly into macro G75. 75. I repeat, these are demonstration or educational software. They have limitations or small differences. The F01 predicts it. F01 is expected to be inserted before the macro, but as I wrote, it works on a CNC. Let's see it in a single block. Here I move to X152, Z31, and set the feed. You see that I don't go down to X125, but to X146. I detach at X148, 1 millimeter radially, so too. I go down to X140, and I detach at X142, 8 1mm radially, so 2. I go down to X140. I detach at X142. I go down to X134. I detach at X136. I go down to X128, and it's determined by P. I go up, and finally reach X125. I go back to 152, read Z31, which will become -31, -5. Here it's already divided. You see, it's not exactly, well, it's not like I told you before, but this goes from CNA to CCNC. He took the 5,000 millimeters and divided it by the distance that's there. Between Z31 and Z70, the division was fair, showcasing great reasoning and logic, which is crucial for ensuring balanced operations. Some CNC machines, however, operate differently. They move incrementally by 5,000 units each time, and then the final move takes whatever distance is left to cover, ensuring no material is wasted. At this moment, we have the capability to press start and completely finish our groove by making modifications to these two specific parameters, which are essential for achieving the desired outcome. This adjustment will result in a different cycle, optimizing the process. For instance, if we set the value to 1000 here to alter the data, it becomes evident that a groove is being created through numerous passes, demonstrating the machine's precision. Observe what occurs when I restart the process. You can clearly see the number of movements required, highlighting the efficiency of the operation. This is very apparent. If we rotate the piece according to the X and Z axis, and then instruct the system to display the toolpath, notice how the Q value changes, reflecting the adjustments made. Since we're exploring examples, let's hypothetically stop editing and set Q to 8000. Then simulate restart and start again. What do you observe? The Q value exceeds the thickness of the insert, resulting in excess material, which can be advantageous in certain scenarios. This technique is particularly useful when you need to create 10 grooves, each 2 mm wide, with a 2 mm blade, spaced 2 mm apart. By setting Q to 4000, you will see that we have successfully created 10 grooves, or whatever the required number is, with excess material between each groove, allowing for flexibility in design. This method is applicable when dealing with small grooves, serving as a handy trick to enhance the machining process. Now, let's proceed with the task. Let's modify our tool settings and specify that the width is 2 mm. This adjustment ensures precision and accuracy in the machining process, allowing for optimal results. By understanding the intricacies of these parameters, we can achieve the desired outcome efficiently and effectively. The ability to manipulate these settings provides us with greater control over the machining process, ultimately leading to improved performance and quality of the final product, which is the ultimate goal in any manufacturing operation. Okay, just close it. Let's go to edit and tell it that this is 4000. We alter, simulate, restart, and then start. You see? Then we'll have to carefully profile everything if we need to make some chamfers, but even there, we thoroughly profile one, create a subprogram, and then move 4 mm with the origin. We'll repeat our subprogram, which we'll analyze in detail in a following video, just like we'll analyze how to repeat cycles in a way that serves our design, our program. Alright, so we've covered G70. Forget about the name here. I copied an existing program. We've tackled G74 and G75. We know how to. Rough, drill, and thread. We can already do a lot of things, but we don't even know 30% of what a good programmer or lathe operator should know. So arm yourselves with a lot of patience if you want to stick with me. Thank you all, and I ask you for a favor. Please share these videos on your social media. It would mean a lot to me. Have a great day.